You see, before we drift too far into the dark tonight, let me ask you something. Something small, well, something that grows larger the longer you think about it. What does it mean when the impossible suddenly appears in the sky? Because that's what James Webb has shown us, an object so strange, so, out of place, that it forces us to rethink not just the universe out there, but the universe in here, in our own assumptions about how things ought to be. Imagine it with me. The cosmic dawn, only a few 100 million years after the Big Bang. The universe still young, still cloudy with hydrogen and helium, still trying to find its own shape. And yet, there it is. A supermassive black hole, 400 million times the mass of our sun. 400 million. At a time when most galaxies were barely finding their feet. And, well, the strangest part? It seems to be sleeping. Quiet. Almost serene. Like a giant that hasn't yet realized its own size. So I keep asking myself, and maybe you're asking too, how does something so big exist so early? And, why is it silent? And if the universe presents us with something that shouldn't be possible, then, well, perhaps it's the universe's gentle way of whispering, it's time to rewrite the story. Because the universe does that. It doesn't just show us beauty. It shows us beauty that forces us to change our minds. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. And, since you and I are wandering through these early cosmic mysteries together, tell me, where in the world are you listening from tonight? It's always fascinating to see who's joining us from all around the world. So let's continue. And, if we close our eyes for a moment and let the mind drift backward through time, we eventually arrive at a place where the universe itself was young. A place where the first galaxies were still stretching their luminous arms into the dark. A place where light was only beginning to find its way across the cosmic sea. And well, the strange thing is that even though this era lies more than 13 billion years behind us, James Webb allows us to see it as though peering through a fragile window of time. That, that, is the miracle of observing the universe at what astronomers call the cosmic dawn. A moment roughly 800 million years after the Great Beginning, when the cosmos had finally cooled enough, settled enough, expanded enough for the first stable structures to appear. Before that, everything was haze, a fog of ionized hydrogen and helium, a universe filled not with stars, but with potential, not with galaxies, but with the promise of galaxies. And, well, the term cosmic dawn is more than poetic. It describes a real physical transformation. Before this period, the universe was opaque. Photons scattered endlessly, bouncing between particles like whispers lost in a storm. But during the cosmic dawn, matter thinned, space expanded, and suddenly, almost gently, the universe became transparent. Light could finally travel freely. The cosmos lit up from within. If you imagine standing there, floating in that embryonic space, you would see small galaxies struggling to ignite. Patchy, irregular structures like islands still forming from drifting sand. They were not the grand spirals we see today. They were clumps, flickers, sparks igniting against an immense darkness. So, when James Webb looks into that era, it is not only observing distant galaxies, it is observing time itself. The early universe captured, moment by moment, as it took its first luminous breaths. And that is why the discovery of a supermassive black hole so early in cosmic history feels, almost like an impossibility. Not because black holes themselves are rare, they form whenever massive stars collapse, but because this particular one weighs 400 million times the mass of our Sun. And that is extraordinary for such an early age. Well, let's place ourselves back into that era again. 800 million years may sound like a long time, but on cosmic scales, it is barely the first step of a child learning to walk. The Milky Way as we know it did not exist. Even the heavy elements, the things that form planets and people, were only beginning to scatter through space. And yet, in this primordial ocean of hydrogen, where even the largest galaxies were still tiny, where the universe was chaotic and clumpy, James Webb detected the signature of a monstrous gravitational presence. A black hole so massive that its very existence forces us to rethink the timeline of the universe. You see, the early cosmos was not a calm environment. It was turbulent. Gas clouds collapsed, fragmented, collided. Radiation tore through regions like relentless waves. Temperature fluctuations created pockets of density that pulled material inward. And galaxies themselves were fragile, small, easily disrupted by mergers and starbursts, their structures shifting under the pressure of intense gravitational forces. So, to find any black hole here is already surprising. It means something had collapsed fast enough, early enough, to produce an object with infinite density in the heart of a galaxy that itself barely existed. But to find a black hole of such enormous size at this time is not just surprising. It is bewildering. We must remember that everything has a beginning. Even supermassive black holes. They grow from seeds, usually the remnants of massive stars that lived and died in the first generations. But those seeds are small, maybe a few dozen solar masses. And to grow such a seed to hundreds of millions of solar masses requires time. Lots of time. Time the early universe simply did not have. And, well, this is why astronomers stared at the Webb data with a kind of awe. Something didn't fit. Something was growing too quickly. Something was evolving too fast. To appreciate how strange this is, imagine a child who grows from infancy to adulthood in a single month. We would know instantly that something unusual had happened. Something about the process itself must be different. And in the same way, this ancient black hole tells us that the universe in its youth might have followed rules slightly different from the ones we see today. But let's slow down. Let's breathe with the early cosmos for a moment. The space around us is filled with hydrogen and helium, the first elements. Stars ignite quickly because gas clouds collapse faster in the denser, younger universe, and galaxies form in a wild, almost frantic pattern. Not the elegant spirals we know now, but chaotic assemblages of gas and young stars. The energy is intense. Radiation blazes. Everything is dynamic. And in such a place, well, the birth of a black hole is not difficult to imagine. But the growth of a giant, that is the puzzle. That is the whisper of mystery carried across billions of years of light. You see, and cosmic dawn is important because it marks the threshold where the universe begins to organize itself. It is the great transition between chaos and structure, between the opaque fog of the early universe and the transparent sky we inhabit today. And every discovery in this era affects how we interpret everything that follows. Finding a black hole here is like finding a fully grown tree in a landscape where the first seeds were planted only yesterday. It forces us to reconsider the speed of cosmic evolution. It challenges the equations that describe how galaxies form and evolve. It nudges us toward the possibility that the early universe was capable of behaviors we have not fully understood. And it reminds us, quietly, and perhaps beautifully, that the universe still contains surprises. The more we study cosmic dawn, the more we realize that nearly every assumption we once held must be revisited. Stars formed earlier than we predicted. Galaxies assembled faster than we expected. Dust appeared. Dust made of carbon, silicon, iron, far sooner than models allowed. And now, supermassive black holes too seem to have emerged in ways our theories struggle to explain. So, perhaps cosmic dawn is not simply an early chapter, but a kind of cosmic confession. A period where the universe quietly admits that it was more efficient, more creative, more dynamic than we realized. And, well, Webb allows us to witness that confession with unprecedented clarity. Its infrared eyes see through the stretching of space itself. Because as the universe expands, light from these ancient objects stretches with it, sliding from visible wavelengths into the infrared. Webb is designed to catch those ancient photons, the ones that have traveled billions of years to reach us. In a sense, every image Webb captures is a message from the past, a letter carried across cosmic time. And the message we are receiving now is this: the early universe was not as simple as we once believed. But let's return for a moment to the sheer difficulty of seeing anything from this era. Cosmic dawn lies beyond the reach of ordinary telescopes. Most of its light is redshifted beyond detection, and the structures are faint, fragile, overwhelmed by distance. Webb must pierce not only the darkness, but the stretching of spacetime itself. This makes every discovery precious, every photon a clue, every faint spectral signature a doorway into understanding. And when Webb detected the signs of that sleeping black hole, its gravitational fingerprint, the motion of gas swirling under its invisible weight, it felt almost like an intrusion of impossibility into the realm of observation. A reminder that the most improbable things are often the most important. You see, the timing matters, the placement matters, the context matters. Because everything in the early universe was happening for the first time. The first stars, the first galaxies, the first heavy elements, the first gravitational giants that would eventually shape entire cosmic landscapes. And so, when a black hole of such size emerges here, it forces us to ask not only how it formed, but what role it played in sculpting the galaxies that followed. Well, perhaps that is the beauty of cosmic dawn. It is not just an era of origins. It is an era of questions, an era that compels us to rethink our assumptions about time, growth, structure, and even the boundaries of possibility. And, well, this is where the story begins to bend toward its next chapter. Because if the early universe was capable of producing such a monstrous black hole so quickly, then the next natural question we must ask is simple and profound. How did James Webb detect something that massive, something that silent, across such an unimaginable gulf of time? And that, is where we turn next, toward the infrared eyes of Webb, and the delicate dance of light and motion that reveals the presence of something that, by its very nature, refuses to be seen. And, as we stand at the edge of that mystery, the monstrous black hole asleep at the cosmic dawn, there's an almost instinctive desire to ask how we even saw it. Because black holes, by their very nature, refuse to be seen. They swallow light. They hide behind the event horizon. And well, the one hiding in that early galaxy was not even active. It was silent, dormant, a gravitational giant breathing slowly beneath a veil of darkness. So, how did James Webb, perched a million miles from Earth, detect something that gave off almost no light at all? The answer lies not in brightness, but in motion. Not in what the black hole emitted, but in how it shaped the matter around it. And to understand this, we must begin with the one thing the universe is kind enough to leave us when light disappears: gravity. And, gravity has a signature, a rhythm, a way of sculpting motion that cannot be faked. Gas clouds orbit differently. Stars move differently. Even the photons skimming the edges of the region behave differently. And Webb, with its extraordinary infrared eyes, can see the consequences of that invisible pull. But let's slow down for a moment. Let's picture the problem the way the scientists saw it. The galaxy hosting this black hole is unimaginably far away. Its light has been stretched by the expansion of the universe, stretched so much that what was once ultraviolet, then visible, is now deep infrared. A wavelength the human eye cannot perceive. A wavelength only a telescope like Webb can detect with clarity. And, this redshifting is not merely an inconvenience. It is a gift, because it reveals the age of the galaxy. It tells us how far back in time we are looking. And in this case, Webb was staring across more than 13 billion years, intercepting photons that began their journey when the universe was less than 1 billion years old. You see, the expansion of space turns time into color. The older the light, the redder it becomes. And that is why Webb was built to see in infrared, because that is where the oldest stories hide. But detecting a faint galaxy bathed in ancient light is only the first step. The real challenge is recognizing the fingerprint of a sleeping black hole. And, black holes that are actively eating scream their presence into the cosmos. Gas spirals inward, heats to millions of degrees, emits enormous radiation. These are quasars, brilliant, ferocious, visible across billions of light years. But this one wasn't a quasar. It was quiet. Almost too quiet. And that was what made it so extraordinary. So, how do you detect something that emits almost nothing? You look at what it moves. Inside this early galaxy, hydrogen gas was swirling, sliding, rotating. Not randomly, not chaotically, but in a pattern dictated by an invisible mass in the center. And when scientists separated the light from this galaxy into its spectrum, into its individual wavelengths, they noticed something strange. The spectral lines were stretched and squeezed in ways that revealed high velocities. Gas moving faster than any ordinary young galaxy could explain. Velocities that only a massive gravitational presence could generate. And, Webb is exquisitely sensitive to these shifts. Every wobble, every stretch, every subtle tilt of those spectral lines carries information about velocity. And velocity tells us mass. Not the mass of the stars, not the mass of dust, but the mass of whatever sits silently at the center. So, as astronomers examined the spectrum, they began to see the signature of rotation. Gas clouds whipping round the core at speeds too high for a normal galactic disk. Too fast for the mass of visible stars. Too fast for anything except a black hole. Millions, or in this case, hundreds of millions, of solar masses in size. Well, that is how Webb detected the sleeping giant. Not by its roar, but by the quiet distortion it imposed on everything around it. But Webb's observations go deeper still. When gas circles a supermassive black hole, some of it becomes ionized, energized, excited into emitting specific wavelengths of light. Even if the black hole is mostly dormant, Small amounts of matter drifting too close can briefly light up the region. These emission lines, the broad, stretched shapes of certain wavelengths, are clues. These broad-line emissions spread out because the gas is moving fast. Faster near the black hole, slower further away. And this difference in speed widens the spectral line, makes it blur, thicken, stretch into a kind of gravitational fingerprint. And Webb, with its fine spectroscopic instruments, captured those broad lines with astonishing clarity. But there is another piece of this puzzle. The way the light is shifted does not only reveal motion, it reveals distance. It reveals the precise redshift. It reveals the galaxy's age. And when astronomers processed this data, they realized the galaxy existed only 800 million years after the beginning. That was the moment everything changed. Because detecting a black hole this massive at such an early epoch was not supposed to happen. It breaks almost every timing model we have. And yet, there it was. Its presence undeniable. Its gravity written into the motion of ancient gas. And, well, the clarity of Webb's instruments meant that scientists could measure the velocity profile precisely. The motion was not random. It obeyed a simple law: faster near the center, slower outward. And the shape of this rotation curve allowed researchers to calculate the mass of the unseen object. 400 million solar masses. Let's reflect on that for a moment. This is not just an estimate. It's not a guess. It's the result of fitting physical models to the observed motion, the curve of the gas, the angle of the spectral lines, the width of the emissions, all pointing to a gravitational anchor far too heavy for any known young galaxy. And the fact that it was asleep, producing only minimal radiation, makes it even more impressive. Because if it were active, if it were devouring matter at full force, we might have mistaken its brightness for a quasar. But it wasn't a quasar. It was a sleeper, a dormant colossus waiting in the dark. This subtlety is important. Many black holes in the early universe were discovered because they were loud, quasars blazing at the edge of visibility. But this one teaches us that the universe may be filled with sleeping giants, hidden from view, detectable only through their gravitational influence. And that changes how we interpret the cosmos. If most black holes spend most of their lives asleep, then we may be missing a vast population of them. Quiet, heavy, ancient. But let's return to Webb for a moment. Its sensitivity to infrared is not just technological brilliance, it's necessity. The farther away something is, the more its light is shifted. And for objects beyond a certain distance, visible light is gone entirely. Only infrared remains. Only warmth remains. Only the stretched out remnants of photons that began their journey across expanding spacetime. This is where Webb excels. It turns infrared signals into full spectra. It breaks the light apart like a prism revealing a symphony of wavelengths. And within that symphony are clues to velocity, temperature, chemical composition, density, and motion. The broad-line emissions told us the gas was moving fast. The redshift told us when the galaxy existed. The spectral shape told us the black hole was quiet. And the rotation curve told us its mass. So? The answer to how Webb detected a sleeping black hole is both simple and profoundly beautiful. By reading the movement of ancient light. By listening to the whisper of gravity imprinted in photons older than our world. By observing, with infinite patience, the way matter dances around emptiness. But there is something deeper here, something that moves beyond techniques and spectra. When Webb captured these signals, it wasn't just detecting a distant object. It was watching part of the universe awaken. It was glimpsing the earliest attempts of galaxies to form structure. It was witnessing how gravity began organizing the cosmos into the shapes we now recognize. And, well, as we reflect on this, a new question emerges naturally. One so large, so heavy, that it demands our attention before we go any further. What does it mean for a black hole to weigh 400 million suns at a time when the universe was barely opening its eyes? It forces us to confront size, scale, growth, the very meaning of mass in a cosmos still learning to assemble itself. And that, leads us gently into the next step of our journey, where we try to understand what such an enormous mass truly represents, not just in numbers, but in the bending of spacetime itself. And, when we left off, we were staring at the numbers, those impossible numbers, whispered into our instruments by ancient light. A black hole weighing 400 million suns. 400 million. The mind hesitates there, hesitates the way it does when trying to count the stars scattered across a clear winter sky. And well, that hesitation is natural, because mass on that scale is not just a number, it is a distortion of reality itself. So, perhaps the best way to move forward is to pause and ask a simple question. What does 400 million solar masses actually mean? Not as an equation, not as a statistic, but as a physical presence in the young universe. To give the idea some grounding, let's compare this ancient monster to the black hole at the center of our own galaxy, Sagittarius A, a quiet, almost gentle supermassive black hole weighing in at roughly 4 million solar masses. Even that is enormous by everyday standards. It bends spacetime so strongly that a star called S2 whips around it in an orbit lasting just 16 years. Imagine that, a star completing a full cosmic loop while you grow from childhood into adulthood. But this early black hole, this one James Webb uncovered, is 100 times more massive than Sagittarius A. 100 times the gravitational pull. 100 times the ability to warp the very shape of spacetime. And, well, that comparison alone is enough to make the breath catch. Because our galaxy is old, mature. It has had the full history of cosmic evolution to grow its central black hole. But the one at cosmic dawn had barely begun to exist. It appeared at a time when the universe was still tangled, still forming, still dense with raw hydrogen. And yet it had the mass of 100 Milky Way cores. But let's bring the scale down even further. Most black holes that form from collapsing stars, the ones we call stellar black holes, weigh maybe 10, 20, 30 times the mass of our Sun. They are the corpses of massive stars. Their gravity is intense but small in scale. A stellar black hole can swallow planets, yes, and distort the path of light around it, but it cannot reshape an entire galaxy. A 400 million solar mass black hole can. The difference is not merely quantitative, it is qualitative. Like comparing a pebble to a mountain, or a ripple in a pond to a storm in the ocean. A black hole that massive doesn't just inhabit a galaxy, it dominates it. It dictates its shape, its rotation, the pace of star formation, the direction gas clouds flow, the fate of everything that drifts too close to its gravitational influence. And well, to understand how such an object influences spacetime, we need to talk about the event horizon, that invisible boundary where escape becomes impossible. Not because the pull is too strong in the classical sense, but because spacetime curves inward so sharply that every possible path leads deeper down. For a stellar black hole, the event horizon might span a few kilometers. For Sagittarius A, it is about 12 million kilometers. For the sleeping giant Webb discovered, the event horizon is larger than the entire orbit of Mercury. A sphere of no return so vast that you could tuck multiple star systems inside it. And, well, that is only the beginning. Because the gravitational reach of a black hole extends far beyond the event horizon. The deeper one goes, the faster one must move to avoid falling in. Gas swirls, stars tumble, light bends. And these motions, these distortions, are precisely what allowed scientists to infer its mass. You see? And, the mass determines the curvature of spacetime. The curvature determines the motion of matter. And the motion of matter writes itself into the spectrum of light that Webb receives. But when we think about mass at this scale, something else becomes clear. A black hole of 400 million solar masses would have required a staggering amount of material to assemble. Gas, dust, stars, entire regions of interstellar medium, all of it drawn inward over time, all of it compressed into a point where density becomes infinite. So, the question is not just what such mass means, but how such mass formed. How did the universe, at less than 1 billion years of age, manage to build such an enormous structure? But before we can explore growth, let's sit with the physical meaning of the mass itself. The gravitational field of a black hole increases steeply the closer one gets to the center, but on a galactic scale, the curvature is surprisingly gentle. It guides the rotation of stars the way a deep well guides the motion of water. At the cosmic dawn, galaxies were small, fragile, barely more than luminous clouds of gas. To place a 400 million solar mass black hole inside such a primitive galaxy is to place an anvil inside a soap bubble. It is heavy beyond reason. The galaxy must have felt its presence, must have been shaped by it. A mass that great would influence star formation, drawing material inward, stirring turbulence, igniting bursts of creation and destruction. It would act like a gravitational heart, beating at the center of the early galaxy, pumping energy and structure into its surroundings. And well, its event horizon would be swallowing stars even as it remained mostly dormant. Not dormant in the sense of inactivity, but in the sense that it was not producing the brilliant radiation of a quasar. So why was it quiet? Perhaps the galaxy lacked enough fuel at that moment. Perhaps the black hole had recently gone through a feeding frenzy and was now resting, surrounded by the leftover turbulence. Perhaps it was between cycles of activity. Or perhaps the early universe had ways of feeding black holes that differ from anything we have yet imagined. But regardless, its mass alone tells us something profound. The early universe was not a slow and gentle builder. It was a place of extremes, rapid collapse, violent mergers, catastrophic inflows of gas, processes that can grow black holes not in billions of years, but in tens of millions. And, well, the fact that Webb found such a giant so early suggests that this might not have been a rare exception. It might be a clue to a pattern where black holes, not galaxies, grow first. A pattern where gravity shapes structure from the inside outward, not the other way around. This idea challenges much of the traditional narrative. We used to imagine galaxies forming first, massive structures of stars and gas, and then black holes slowly evolving in their centers. But the presence of such an oversized black hole at cosmic dawn flips that sequence. It hints that the gravitational seeds of the universe may have been planted early and aggressively, shaping the first galaxies as they formed. And if black holes came first, If they were the anchors around which galaxies built themselves, then the universe's architecture begins to look very different. Not a gradual assembly, but a rapid condensation. Not slow growth, but sudden emergence. The 400 million solar mass giant becomes not a puzzle, but a signpost. A marker pointing toward a universe that built structure faster than we expected. Well, perhaps the most astonishing aspect is not the mass itself, but the implications it carries. This black hole's size alone forces us to reconsider how fast black holes can grow, how early they can form, how galaxies assemble around them, how many silent giants may be hiding across the cosmos. And, well, that brings us to something even more subtle. The ratio between this black hole and its host galaxy is wildly unbalanced. In the modern universe, black holes tend to weigh about 1,000th the mass of their galaxy. But here at Cosmic Dawn, the black hole seems to dominate almost 40% of the galaxy's mass. Imagine that imbalance. A tiny, fragile galaxy wrapped around a dense, invisible core that outweighs nearly everything else combined. It tells us that the early universe played by different rules, or perhaps the same rules, but with different initial conditions. Conditions we do not yet understand. This is why mass matters. Because mass is not just a quantity. It is a storyteller. It is a witness to the processes that formed it. And the story this black hole tells is strange, beautiful, and deeply disruptive to our expectations. And well, when we listen closely, really listen, to the mass itself, we hear questions rising like echoes across time. How could something have grown this fast? What fuel could have fed it? What physics allowed such rapid collapse? Does this reveal something new about gravity? Or something new about the way gas behaved in the early universe? These questions carry us naturally toward the biggest tension in this discovery. The tension between what we observe and what our theories predict. The tension between how big this black hole is and how little time the universe had given it. So, after contemplating what this mass represents physically, philosophically, gravitationally, we are led gently, inevitably, toward the next chapter of our journey. The chapter where we confront the central paradox. The universe was too young for a black hole this massive. And yet, there it is. Which means something in our understanding must shift. And that, is where we turn next, toward the greatest inconsistency this discovery reveals, and the beginning of the rewriting of cosmic history. And, as we stand before the paradox that has now fully taken shape, the paradox of a black hole far too massive for its cosmic age, we feel something familiar in the air, something that always emerges when the universe forces us to confront our assumptions. It is that blend of confusion and awe, that quiet realization that the cosmos is not merely vast, but profoundly creative. And well, perhaps this is where the story of this ancient giant becomes even more unsettling, because the deeper we look, the clearer the contradiction becomes. It's not just big. It's not just early. It's impossibly big for impossibly early. So, let's ease into the heart of the problem. Let's look at the timeline, slowly, gently, as if we're turning fragile pages of an ancient manuscript. The universe at this moment, the moment when this black hole existed, was around 800 million years old. That sounds like a long time, of course, but compared to the scale of cosmic history, it is the first breath of the first morning. A dawn light barely rising across the early universe. The models we've trusted for decades tell us something very straightforward. Black holes begin small. They begin as stellar remnants, collapsed cores of massive stars, maybe tens of solar masses, maybe 100. And then, over billions of years, they feed, they merge, they grow. Slowly, steadily. A gravitational hunger stretched across eons. But here, well, here we are staring at something that breaks that narrative completely. Something that tells us that the universe didn't wait billions of years. It built a 400 million solar mass black hole before galaxies even knew how to form properly. You see? And, this is where the paradox becomes inescapable. If you start with a stellar mass seed and you let it eat as fast as physics allows, at the Eddington limit, it simply cannot reach 400 million solar masses in 800 million years. The numbers refuse to cooperate. The math doesn't bend. The timeline collapses under its own weight. So, the black hole Webb found is not just an observational curiosity. It is a direct challenge to how we think the early universe worked. Well, perhaps the simplest way to understand the problem is to think of growth not as mass, but as time. To reach such size, the black hole would need more hours than the universe had experienced. It's like meeting a fully grown tree in a forest where the seeds were only just planted. And, well, this forces us to confront a painful question. Were our models wrong? Or is the universe trying to tell us something new about its earliest epochs? Let's picture the traditional growth pathway for a moment. A black hole increases its mass by swallowing gas and dust, but as it feeds, the material heats up, releasing light, and that light pushes back. Radiation pressure. The more it eats, the harder it becomes to keep eating. This is the Eddington limit, a kind of cosmic braking system. It says, you can grow, but not too fast, not in runaway fashion, not without resistance. And yet, here stands a black hole that seems to have ignored that rule. That seems to have grown, not just quickly, but impossibly quickly. So maybe it didn't start from a small seed. This is the first escape route scientists consider. Maybe the early universe had a different kind of seed, a massive one, something far larger than the remnants of ordinary stars. And well, this idea leads us down an extraordinary path. Because if the first stars, the so-called population 3 stars, were enormous, hundreds of times the mass of the Sun, then their collapse might produce larger black hole seeds. Not 10 solar masses, but a few hundred, maybe even 1,000. But even those numbers fall short. Even starting with 1,000 solar masses, the growth timescale remains too short. The black hole Webb detected still grows too fast. It still outpaces what physics comfortably allows. So, we take another step outward, another hypothesis, another attempt to bridge the impossible. Direct collapse. The idea is bold but elegant. Instead of forming from a star, perhaps enormous clouds of hydrogen collapse directly into black holes. No supernova, no star, no fusion, just gravity overwhelming everything at once, forming seeds as massive as 100,000 solar masses. That changes the math significantly. With such a seed, the path toward 400 million solar masses becomes more reasonable. Not easy, not trivial, but possible. The timeline stretches into something slightly less contradictory. And, well, direct collapse is more than theory. Simulations support it. The early universe, filled with dense gas and intense ultraviolet radiation, might have created pockets where star formation was suppressed, forcing clouds to collapse into massive black holes instead. But even then, even with seeds 100,000 solar masses large, the observed black hole still pushes the limits. It still grows too big, too fast, too early. And so, we arrive at the heart of the cosmic tension. Perhaps the earliest black holes didn't grow steadily. Perhaps they grew in violent bursts. Perhaps they fed at rates far beyond what the Eddington limit predicts. Super Eddington accretion. It's not an idea we propose lightly, because it requires matter to fall inward so chaotically, so rapidly, that radiation pressure cannot push it away. Clumps of gas, thick flows, inflows so dense that light becomes trapped inside, swallowed along with the matter itself. And in such a scenario, a black hole can grow not just quickly, but explosively, 10 times faster than the traditional limit, maybe more. This would allow a black hole to balloon in mass during short, intense episodes, and that might explain how a sleeping giant could exist so early. Grow fast, then quiet down. Grow fast again, then sleep. But wait, this introduces a new paradox. If a black hole is feeding at such extreme rates, it should be luminous, brilliant, blazing across the cosmos like a miniature quasar. And yet, the black hole Webb discovered is not luminous at all. It is silent, dormant, a sleeper. Well, perhaps the solution lies not in constant feeding, but in cycles. Bursts of rapid growth followed by long periods of stillness. A cosmic heartbeat. A binge and sleep pattern that lets the black hole grow in episodes while spending most of its life quiet. But, this is where the contradiction intensifies once more. The more we study this black hole, the more the universe feels like it's telling us that the early epochs were far more extreme and far more creative than we ever expected. You see, there is something remarkable about cosmic dawn. Everything is faster, denser, more chaotic. The first galaxies are irregular. Gas flows are turbulent. Radiation fields are fierce. Mergers are common. The conditions for rapid black hole growth may simply have been far more favorable than in the later universe. So, when we say the black hole is too big for its age, perhaps what we truly mean is that our understanding of that age is incomplete. That the physics of the early universe contained pathways we have not yet fully explored. Try to imagine a galaxy in that era. Not a stately spiral like the Milky Way, not an elongated elliptical, but a messy, collapsing clump of gas, constantly merging with its neighbors, constantly funneling material toward its center. In such an environment, a black hole might gorge itself at rates unseen in the modern universe. And yet, despite all these possibilities, despite direct collapse seeds and super Eddington inflows and chaotic mergers, the paradox lingers. Because to reach 400 million solar masses still requires a nearly perfect sequence of events. Everything must align. Everything must cooperate. And, well, that's what makes this discovery so unsettling. Not that the black hole is impossible, but that it requires the universe to be more efficient than we assumed, more aggressive, more prolific. The cosmic dawn must have been a period of accelerated evolution, a period where gravity sculpted complexity at breathtaking speeds. So what does this tell us? First, that our models of black hole growth need refinement. Not replacement, refinement. They need to account for the extreme conditions of the early universe. They need to allow for rapid growth pathways that fade as the cosmos expands and cools. Second, that massive seeds may have been common. Direct collapse may not be a rare event. It may be a foundational mechanism in the earliest stages of cosmic structure. Third, that Eddington-limited accretion, the slow, steady model, may not apply universally. The early universe may have routinely crossed that threshold. And finally, well, it tells us that cosmic history is more dramatic than the gentle narrative we once imagined. The universe was not cautious in its youth. It was bold, ambitious, creative. And that creativity produced giants long before it produced order. So, as we contemplate this paradox fully, sinking into the depth of what it means for a black hole to be impossibly massive, impossibly early, we feel the next question rising naturally in the silence. If this black hole grew so fast, too fast, then what physical processes allowed it? What mechanisms shaped its evolution? What forces bent the rules we thought were fixed? And that, leads us gently toward the next chapter, where we explore the physics of growth itself, the limits, the violations, and the hidden pathways the early universe may have used to build a giant before its time. And, as we step from the paradox of impossible mass into the deeper question of how such a giant could have grown so quickly, we find ourselves entering a landscape where physics feels less like settled truth and more like a set of tentative footprints across soft cosmic sand. Because, well, once we admit that the numbers refuse to fit within the traditional models, we are invited, or perhaps compelled, to explore growth mechanisms far more violent, far more chaotic, and far more imaginative than anything we usually consider. So, let's begin gently with the simplest idea, the one we sketched only in outline before: accretion, the swallowing of matter, the slow rain of gas falling inward, the steady feeding of a black hole surrounded by a turbulent disk of hydrogen and helium. Accretion is the heartbeat of black hole growth. But in the early universe, that heartbeat may have quickened to something wild, something approaching a cosmic fever. Imagine a galaxy at cosmic dawn. It is not calm, it is not elegant. It is a swirling cloud of raw material collapsing under its own weight. Gas everywhere, stars forming rapidly, radiation bursting outward in powerful winds. In such a place, the center, already occupied by a black hole seed, becomes a gravitational drain. Gas funnels inward along filaments that stretch across light years. Streams of matter spiral in like water down a colossal drain. And, well, when material falls inward, it heats, it glows. It forms an accretion disk so hot that atoms split apart, electrons dance free, radiation blasts outward. And yet, the black hole grows. It eats. It gathers mass from every direction, pulling entire streams of gas into itself. But the Eddington limit, the upper bound of how fast a black hole can safely feed, still stands in its way. The more it eats, the brighter it becomes. And the brighter it becomes, the more radiation pushes back on the incoming gas. A kind of cosmic braking, a natural moderation. So how could this ancient black hole outrun that limit? Well, perhaps it didn't respect the limit at all. One pathway is what scientists call super Eddington accretion. Instead of material flowing in smoothly, like water through a pipe, it arrives clumped, chaotic, thick with density. In such a turbulent flow, radiation becomes trapped within the infalling matter, unable to escape upward. And if the light cannot escape efficiently, it cannot push the gas outward. The black hole, in effect, becomes shielded by its own food, allowing it to gorge itself at 10 or 100 times the typical rate. It's a messy, violent growth. Not elegant, not uniform. A sudden avalanche rather than a steady rain. And if this ancient black hole experienced even a few of these episodes, each lasting perhaps a few million years, its growth could leap forward dramatically. But super Eddington feeding requires specific conditions, conditions more common in the early universe than in later eras. Dense gas, non-linear turbulence, rapid collapse, a feeding zone almost drowned in material. This paints a picture of the early cosmos as a kind of gravitational feeding frenzy. Not sustainable, but episodic. Bursts of rapid growth followed by quiet periods. That pattern fits the strange duality we observe, an impossibly massive black hole that is currently dormant. But accretion alone may not be the full story. So, we turn to another mechanism, mergers. Galaxies in the early universe did not drift peacefully apart. They collided. They merged. They tore into each other with a kind of developmental violence that shaped the cosmos into what it would eventually become. And when galaxies merge, their central black holes can merge as well. Imagine two early galaxies, small, irregular, gas-rich, colliding in the dark. Their stars scatter, orbits distort, clouds of gas compress, triggering waves of star formation. And deep in the centers, embedded in the gravitational chaos, two black holes spiral inward, losing energy through gravitational waves, inching closer until they finally combine into a larger whole. And, well, mergers do something that accretion never can. They add mass instantaneously. They skip the feeding step. A 10,000 solar mass seed merging with a 50,000 solar mass seed becomes 60,000 in a single cosmic heartbeat. In a universe filled with small, chaotic galaxies merging frequently, black hole mergers could have been common, especially if massive seeds existed from the beginning, especially if direct collapse was creating many large black holes in the same era. But mergers alone cannot explain everything. They can help, but they require a population of black holes already existing. They can push the mass upward, but they cannot create the initial seeds. And once again, the timeline becomes tight. So, perhaps the most radical mechanism must enter our discussion. The idea that black holes could form directly from collapsing supermassive stars. This is a strange but fascinating idea. A supermassive star, 1,000,000 times the mass of the Sun, forms in a dense region of primordial gas. These stars would be unstable, powered by rapid nuclear fusion, but unable to maintain equilibrium. And instead of exploding as supernovae, they would collapse inward almost instantly, forming gigantic black hole seeds. This idea sidesteps the timescale problem. If the black hole begins its life already weighing 100,000 solar masses, then even modest growth afterwards can yield giants quickly. And it suggests a universe capable of producing objects we can hardly imagine. Stars so massive that they lived brief, intense lives, collapsing not into neutron stars or stellar black holes, but directly into seeds that would become the supermassive giants we observe today. But well, we still cannot escape the gravitational puzzle. Even with these possibilities, even with mergers and supermassive seeds and chaotic accretion, the black hole Webb discovered pushes every model to the limit. Which leads us to a more philosophical question. Perhaps growth in the early universe wasn't governed by the same constraints that govern growth today. Perhaps the universe itself was different, denser, hotter, full of gas clouds collapsing faster than modern galaxies can manage. And, well, maybe the physics wasn't different, but the circumstances were. You see, and, in a younger universe, gravity was more efficient. Gas had not yet been disrupted by supernovae or enriched with heavy elements that complicate cooling. Hydrogen and helium, the simplest elements, cool efficiently under compression, allowing gas clouds to collapse rapidly toward their centers. The early universe may have simply been better at feeding black holes. But if that is true, then something else follows naturally. Black holes might have shaped galaxies instead of galaxies shaping black holes. It's not just a reversal of cause and effect. It's a restructuring of cosmic evolution. If black holes formed early, grew fast, and became enormous while galaxies were still tiny, then galaxies may owe their shape, their rotation, their stability to the gravitational anchors inside them. Imagine the early galaxy hosting this 400 million solar mass monster. It would not act like a tranquil spiral. It would be unstable, swirling violently around a massive core. Gas clouds would fall inward. Star formation would ignite and extinguish in waves. The black hole would influence everything: structure, temperature, motion, and evolution. So, growth is not just a matter of swallowing matter. It is a matter of shaping the galaxy around it, altering the flow of gas, changing the distribution of mass, dictating the life cycle of early stars. Perhaps the black hole grew quickly because the galaxy itself was feeding it. And perhaps the galaxy evolved the way it did because the black hole demanded it. A kind of feedback, a gravitational dance, each shaping the other. And, well, this brings us toward another possibility: cosmic filaments, the vast threads of dark matter and gas that make up the large-scale structure of the universe, might have played a crucial role. In the early universe, these filaments were dense and narrow, acting like cosmic rivers funneling material directly into young galaxies. If a black hole sat at the junction of several filaments, it could receive a constant inflow of cold gas. And cold gas is the most efficient fuel for black hole growth. It plunges inward easily. It radiates less. It resists being blown away. It provides a steady, uninterrupted supply of mass. And, if this ancient black hole lived in such a privileged location, at the crossroads of cosmic filaments, its rapid growth becomes less mysterious. It becomes almost natural. But then, another problem emerges. If rapid growth was natural, why don't we see countless black holes like this in the early universe? Why does this one stand out? Is it an outlier? A rare giant? Or the first of many we have yet to discover? These questions still trouble astronomers, and they lead to the possibility that we have only glimpsed the beginning. That JWST, with its extraordinary sensitivity, may reveal dozens or hundreds of massive black holes where no theory predicts they should exist. And if that is the case, well, then we must rewrite the story of cosmic dawn completely. We must accept a universe that assembled its largest structures early, not late. A universe where black holes grew rapidly, not gradually. A universe more dynamic and more ambitious than the one described in older models. So, growth is not a single story. It is a tapestry. Accretion, mergers, direct collapse, supermassive stars, filamentary inflows, super Eddington episodes, all woven together into a complicated, thrilling narrative. And the giant web discovered is a testament to that narrative, a sign that the early cosmos was filled with processes we are only now beginning to understand. And, well, as we stand at the threshold of these growth scenarios, feeling the gravity of each hypothesis pulling us in different directions, a new question begins to rise in the quiet. If this black hole grew so fast, then where did it begin? What seed allowed it to leap ahead of the universe itself? And, that question of origins, of beginnings, of the very first collapse, leads us naturally, irresistibly, into the next chapter, where we search for the seed that could become a giant before the universe had even learned to walk. And, as we drift from the furious physics of growth into the softer, stranger idea of a cosmic rhythm, this binge and sleep cycle the early universe may have woven into the very nature of black holes. Something shifts in the way we see these ancient giants. Because, well, when we imagine a black hole, we often picture an unending hunger, a gravitational maw swallowing matter ceaselessly, endlessly. But the evidence James Webb is returning suggests something else, something slower, something more alive, a pattern, a pulse. So, perhaps the right way to begin is with that gentle contradiction. The black hole we have been studying is enormous, monstrously so. But at the time Webb observed it, it wasn't eating at all. It was quiet, still, dormant, and that. Silence is the very clue that helps us understand how it grew so quickly in the first place. Imagine, for a moment, a creature in the early universe that does not feed constantly, but in violent spurts. A few million years of furious, unstoppable consumption, matter rushing inward, radiation trapped, accretion disks bright and chaotic, the Eddington limit shattered over and over, then a long, heavy sleep. 100 million years of silence, a cosmic winter, no light, no roar, just gravity holding its breath. And, well, this pattern is not speculative poetry. It emerges naturally from the physics of early galaxies. When the gas supply is dense and chaotic enough, black holes can enter phases of runaway accretion. But those phases exhaust the fuel rapidly. They collapse the environment around them. They clear out the central region of the galaxy. The very act of feeding destroys the conditions required for continued feeding. This is why black holes sleep. They sleep because they have eaten too much. They sleep because their own energy, jets, winds, radiation, has swept the galaxy clean of food. We see this in simulations. We see it in modern quasars. We see it in the delicate balance between radiation pressure and infalling gas. And James Webb is now showing us that we may be seeing the same thing at the dawn of time. But let's slow down. Let's breathe with the universe again. The binge and sleep model feels almost biological, almost like a heartbeat. 5 or 10 million years of violent growth. Then silence. Then another burst when new gas falls in from cosmic filaments. Then silence again. And, well, when you stack enough of these episodes together, if the universe provides just the right timing, the result is a black hole that grows far faster than one that feeds smoothly and steadily. That is the irony hidden within this cosmic rhythm. It's not constant hunger that fuels the biggest giants. It's intermittent, chaotic hunger. So, let's picture the early galaxy hosting this ancient black hole. Each binge would have transformed the environment. The first burst of growth sends out winds traveling thousands of kilometers per second. These winds sweep away the inner gas. They halt star formation. They heat the galaxy. They carve out cavities. And then, when the black hole sleeps, the galaxy is allowed to regrow its gas reservoir. Slowly at first, then rapidly as the filaments of the cosmic web deliver fresh material. And once enough gas has returned, the black hole wakes again, almost instinctively. Light erupts. Jets fire. The accretion disk brightens. The black hole swells in mass. The cycle repeats. And that gives us a picture of a universe with rhythms of creation and destruction. The black hole grows. The galaxy suffers. The galaxy recovers. The black hole awakens. The galaxy is reshaped again. It's not a clean process. It's not orderly. It's chaos with memory. And, the sleeping giant Webb observed happens to be caught in the long, quiet winter of that cycle. It has fed recently enough to be enormous, but long enough ago that its environment has settled into silence. This explains its contradictory nature. Too big, yet too quiet. Too young, yet too evolved, too massive, yet dim at the moment of observation. The binge explains the size. The sleep explains the silence. And, well, if we look deeper at the physics, the picture becomes even more fascinating. During the binge phases, the accretion flow becomes optically thick. Light cannot easily escape. It is trapped, dragged inward along with the gas. This means the black hole can grow faster than the Eddington limit allows, because radiation cannot push back effectively. That trapped light becomes part of the meal. But once the gas is expended, once the environment is cleared, the accretion disk collapses. Temperatures drop. Emission fades. The black hole becomes invisible. It sleeps. It waits. And you see, this is precisely the state Webb captured. A giant between meals. So, why does this matter for cosmic history? Because this cyclical growth model implies that the early universe was rich not just with black holes, but with black holes whose active phases were brief and rare. Statistically, we are far more likely to observe them asleep than awake. This means the early universe may have been filled with giants we have not yet detected. Giants that grew rapidly, but emitted little light most of the time. Giants whose existence remains hidden because we are catching them in their long periods of silence. It also means that our census of ancient black holes is dramatically incomplete. We see the bright ones, the quasars. We do not see the sleepers. The Webb discovery may be the first of many silent giants waiting to be revealed by gravitational and spectroscopic signatures rather than luminous outbursts. And, well, the binge and sleep cycle also changes how galaxies grow. If black holes undergo rapid bursts of activity, they can suppress star formation repeatedly. A galaxy may attempt to grow, only to be blasted apart again and again. This creates galaxies with unusual star formation histories, galaxies that appear prematurely aged, prematurely quenched. So, this means the sleeping black hole reveals more than its own life cycle. It reveals the life cycle of its galaxy. The scars of earlier binges are written into the low star formation rate Webb observed. It is a galaxy that has been shaped, regulated, controlled by its central giant. And well, this brings us to one of the most poetic aspects of modern astrophysics. Galaxies and black holes evolve together, each influencing the other in ways more intimate than we once imagined. The galaxy feeds the black hole. The black hole regulates the galaxy. Not just, but also, the galaxy's ability to form stars and retain gas. It's not out there. It's in here, within the very structure of the galaxy itself. The story of the black hole is the story of the galaxy. Their destinies intertwined. This changing of rhythm, from binge to sleep, also hints at something larger. The universe itself may have had a biological feel in its earliest eras. Not life, of course, but cycles. Growth, collapse, regrowth. A kind of cosmic respiration. When the black hole fed, it exhaled energy into the galaxy. When it slept, it inhaled matter again. A steady oscillation across millions of years. We grow older. Clocks tick. But in the cosmos, time stretches these breaths into epochs. And, as strange as it may sound, this rhythm solves many of the paradoxes we've been struggling with. It explains the immense mass. It explains the silence. It explains why galaxies in the early universe often appear oddly small, oddly quenched. But there is a deeper question hiding beneath all of this. If this binge and sleep cycle was common, if early black holes fed repeatedly and violently, then the early universe must have been filled with extreme bursts of energy, jets blasting, wind sweeping, radiation surging. How did all of this energy shape the structure of the cosmic web? You see, and this is where the story bends toward cosmology, toward the large scale. Because if early black holes were active in cycles, they could have contributed to the heating of intergalactic gas. They could have influenced when and how the universe became fully transparent. They could have altered the rate at which galaxies formed along the filaments. So, the binge and sleep model is not just a way to explain one black hole. It is a model that could reshape our understanding of cosmic dawn entirely. And perhaps this is the most beautiful part. This model explains not only the black hole's growth, but its personality, its temperament. It becomes not just an object, but a rhythm, a presence, a repeating pattern etched into spacetime. And, well, as we let this idea settle, a final thought emerges, leading us gently toward what comes next. If black holes lived in these cycles, if they breathed in bursts, then the next natural question is this: what did these bursts do to the galaxies around them? How did the jets, the winds, the radiation reshape everything? And that, leads us directly into the next chapter, where we shift our focus from the black hole itself to the galaxy it inhabits, and to the strange, disproportionate relationship between them, where mass becomes imbalance, and imbalance becomes a clue to the deeper story the early universe is trying to tell. And, as we drift from that cosmic rhythm, the binge and sleep heartbeat of a young black hole, we find ourselves staring at something just as strange, perhaps stranger still: the imbalance, the disproportion, the quiet, unsettling truth that the galaxy hosting this ancient giant is far too small for the monster sleeping at its center. And well, once we begin to understand this imbalance, the universe starts to whisper a deeper story. A story not just about growth, but about architecture, how galaxies are built, and how sometimes they are bent, reshaped, or even consumed by the very objects they cradle. In the modern universe, we see a pattern, a rule of thumb so consistent that astronomers treat it almost like a cosmic law. In a typical galaxy, the central black hole weighs about 1,000th of the galaxy's total stellar mass, roughly 0.1%, a balance, a harmony. The black hole sits in the middle like a conductor guiding an orchestra, powerful, yes, but never overwhelming. Never too large, never the dominant weight. But here, and well, in this early galaxy, the rule is shattered completely. The black hole is not 1,000th of the galaxy's mass. It is not 1%. It is not even 10%. It is 40%. 40. The moment one says it aloud, something in the mind hesitates, stutters, repeats, because that number breaks more than a pattern. It breaks our sense of proportion. Imagine the Milky Way containing a 400 billion solar mass black hole instead of a 4 million one. Imagine a galaxy where the center outweighs the stars, the gas, the dust, the spirals. A gravitational monarch sitting on a throne too large for its kingdom. That is what Webb has shown us. And, that imbalance forces us to consider possibilities that feel almost mythic, yet remain grounded in serious cosmological theory. So, Perhaps the first and most intriguing scenario is direct collapse. The idea that instead of forming from stars, a massive cloud of primordial gas, vast, pristine, untouched by heavy elements, collapsed straight into a black hole seed weighing 100,000, perhaps even 1,000,000 solar masses. If that seed began its life so monstrously large, then the galaxy forming around it may simply have been late to the party. The black hole grew quickly, while the galaxy struggled to assemble itself, fighting turbulence, fragmentation, radiation, and the feedback of its own central giant. In that case, the imbalance is not a sign of something broken. It is a sign of something beginning. A galaxy still in its infancy, still gathering mass, still flowing along the filaments of the cosmic web. And we may be catching it at the exact moment of disproportion before the galaxy grows into itself. But direct collapse is only one possibility. And, well, another scenario emerges from the idea of stripping, galaxy stripping, a process as violent as it sounds. Two galaxies dance too close. One is torn apart by tidal forces. Gas is siphoned away. Stars are flung outward. And the survivor is left far lighter than before, like a tree stripped of its branches. If this sleeping giant once lived in a much larger galaxy, one that has since been shredded, its mass would no longer seem so disproportionate. The black hole would not have grown too large. The galaxy would have become too small. But, this explanation carries its own problems. We see no immediate signs of a recent galactic collision, no clear tidal tails, no debris trails luminous enough for Webb to easily detect. And yet, at this distance, at this redshift, the universe is murky, dusty, blurred by time itself. The evidence may be hidden from us, dissolved into the darkness. So, there remains a third possibility, a surprisingly elegant one. The galaxy is still growing. Perhaps the black hole reached its incredible size early, through super Eddington feeding or massive seeding, while the galaxy simply hasn't caught up yet. It is not done forming. It is not finished acquiring gas. It is not finished building stars. In that case, this imbalance is not an error. It is a snapshot, a moment in a long cosmic evolution, a pause in a process that spans billions of years. Imagine a galaxy caught mid-breath. The black hole has already completed its early cycles of binge feeding, but the galaxy, having been blasted repeatedly by those energetic outbursts, is still slowly recovering, still gathering material, still rebuilding its star-forming clouds. The imbalance is temporary, an artifact of timing. And, this is a humbling thought, because it reminds us that the universe is not static, not fixed, not a collection of objects sitting quietly in space. It is a story unfolding so slowly that when we catch a single frame, we risk misunderstanding the whole. But regardless of which scenario turns out to be true, direct collapse, stripping, delayed growth, the imbalance tells us something profound about the early cosmos. It tells us that black holes did not merely sit in galaxies. They shaped them, molded them, controlled them. It's not out there. It's in here, woven into the very skeleton of galaxy formation. That 40% ratio speaks to a universe where structure formed from the inside outward, where gravity took root in tiny pockets and grew rapidly, pulling material inward, forcing galaxies to evolve around dense, central anchors. And, well, this changes how we think about cosmic evolution itself. The traditional picture shows galaxies forming first, with black holes slowly emerging at their centers. But the evidence we're seeing now hints that perhaps the reverse is true. Perhaps black holes were the seeds, and galaxies the fruit. You see, when we accept that possibility, the universe suddenly feels more interconnected than ever. Black holes and galaxies grow together, not in harmony, but in tension, in imbalance, in cycles of disruption and rebuilding. The black hole grows, the galaxy shrinks, the black hole sleeps, the galaxy regathers. So, when Webb reveals a galaxy where nearly half its mass is locked inside a silent, invisible center, it is not showing us an anomaly. It is showing us a universe in the middle of becoming. And perhaps that is the quiet beauty of this discovery. It teaches us that cosmic laws, like the mass ratio rule, are not universal truths carved into spacetime. They are outcomes, endpoints, patterns that emerge only after billions of years. But in the early universe, in the era of first stars and first galaxies, those patterns had not yet been written. And, well, if the black hole to galaxy mass ratio was radically different then, what else might have been different? What other relationships might have been inverted, exaggerated, reversed? It is a question that nudges us forward, a question that pulls us toward the next part of this journey. Because if the imbalance reveals how galaxies formed around their giants, then the next step is to understand how those giants shaped the galaxies in return. How their energy, winds, jets, radiation, swept through the young cosmos, quenching star formation, sculpting matter, altering destinies. And that, leads us gently, naturally, into the next chapter, where we step into the realm of feedback, where the sleeping giants of cosmic dawn reveal that even in slumber, they reshape the universe around them. And, as we step from that strange imbalance between the black hole and its fragile little galaxy, the story deepens in a way that feels almost, unsettlingly inevitable. Because, well, when a black hole grows too quickly, when it rises to dominate nearly half the mass of its host, it cannot help but reshape everything around it. It is not just a passenger in that galaxy. It is the engine, the sculptor, the violent heart. So, perhaps this is the moment to finally talk about feedback. Not feedback in the human sense of gentle correction, but feedback in the cosmic sense, where the energy released by a feeding black hole sweeps outward and alters the destiny of an entire galaxy. And, the first thing to understand is that when a black hole enters one of its binge phases, it becomes profoundly bright. Light pours from the accretion disk, winds erupt from the hot plasma, and sometimes jets, narrow beams of material accelerated to nearly the speed of light, launch from its poles. These jets are not metaphors. They are violently real. They tear through space like spears of radiation. Imagine being inside a small, young galaxy while that happens. You would see winds moving outward at thousands of kilometers per second. You would watch gas, the very thing needed to form stars, being blown away. The galaxy would thin. It would struggle to grow. Star formation would falter. And that is exactly what the observations of this galaxy show us. A star formation rate far lower than it should be. A galaxy quieter than expected. A population of young stars that seems prematurely exhausted. And, well, the simplest explanation is that its own central black hole has repeatedly quenched it. Each feeding burst sent shock waves outward, clearing the inner regions of gas. Each period of sleep allowed some gas to return, but never enough. Never enough to rebuild the galaxy fully. never enough to grow at the rate a normal young galaxy should. This is the essence of feedback. The black hole grows. The galaxy shrinks. The black hole sleeps. The galaxy whispers back into existence. Then the cycle repeats. And when we step back, when we look at this process with a wider gaze, we realize something quietly profound. Black holes can kill galaxies. Not literally kill, of course, but they can halt the process of star formation that breathes life into a young galaxy. A galaxy without star formation is like a forest without seedlings. It does not grow. It only ages. So, this ancient galaxy, sitting so close to the dawn of time, is already showing signs of having been burned out early. A dead or dying galaxy at an age when galaxies should be bursting with new stars. That is the paradox Webb has revealed. That is the signature of feedback. But let's slow down. Let's breathe with the physics again. How exactly does a black hole quench its galaxy? Well, the first mechanism, the most gentle, if such a word can be used, is radiation pressure. The accretion disk glows fiercely as matter spirals inward, and the light itself exerts pressure. Photons push. They shove gas outward. They heat it. They make it harder for clouds to collapse and form stars. Then comes the second mechanism. Winds. Not the breezes of Earth, but enormous, turbulent outflows. Gas whipped outward by magnetic fields and intense heating. These winds can escape the central region, spreading through the galaxy, carrying away the raw materials of creation. And third, the most dramatic, are jets. Collimated beams of matter and magnetic fields that shoot from the poles of the black hole, accelerating close to the speed of light. These jets can extend far beyond the galaxy, punching holes in its gaseous halo, stirring turbulence, heating the intergalactic medium, disrupting the quiet flow of gas that would otherwise cool and form stars. And, well, this mixture, radiation, winds, jets, is the vocabulary of black hole feedback. It is how black holes speak to their galaxies, not softly, but forcefully, not gently, but with an intensity that can reshape entire regions of space. Now picture all of this happening not over billions of years, but in the first few 100 million years of the universe. Everything is denser. Everything is more fragile. Everything is more sensitive to disruption. A single feedback episode could quench an entire galaxy. And Webb is showing us evidence that something just like that occurred. The galaxy around this 400 million solar mass black hole is small, underdeveloped, starved. It is not catching up to the black hole. It is falling behind. It is living in the shadow of a giant that grew too quickly, perhaps too aggressively. So, the feedback explanation illuminates not only the galaxy's weakness, but the black hole's strength. It explains why the galaxy is small, why it has low star formation, why it looks prematurely old. The black hole has reshaped it from the inside out, but the effects may be even larger. Feedback from early black holes might also have shaped the large-scale structures of the early universe. Their winds could have heated the cosmic web, slowing the collapse of gas into nearby galaxies. Their jets could have ionized regions of space, influencing the reionization era. Their energy could have changed the timing of cosmic dawn itself. It's not out there. It's in here, hidden in the very design of the cosmos we see today. And, well, this is perhaps the most stunning realization. The smallest galaxies near the beginning of time may have been governed by their black holes, not the other way around. The giants at their centers dictated the fates of the stars around them. This flips our understanding. It reverses the hierarchy. It rearranges the skeleton of cosmic evolution. So, what does this mean for the big picture? For the story we are trying to piece together? It means the early universe was filled with galaxies that lived fast and died young. Galaxies that were quenched early. Galaxies that were sculpted into strange shapes by their central giants. And many of these galaxies would later merge, forming larger systems. Systems that carry the signatures of ancient feedback buried in their structure. And, perhaps even more importantly, it tells us that the number of massive black holes in the early universe is likely far greater than we once imagined. Because if most of them spend 90 or 95% of their time sleeping, dim, silent, invisible, then we would only catch them during rare episodes of activity. Most early black holes might be hiding right now, invisible to our telescopes, unless we look not for their light, but for their gravitational influence. And, well, that leads us naturally toward the next mystery. If black holes shaped galaxies so profoundly in the early universe, if they quenched them, starved them, sculpted them, then what does that say about the population of sleeping giants we have not yet seen? How many are out there? How many shaped their galaxies before retreating into silence? How many remain hidden inside faint, quiet systems waiting for us to detect them? And that, brings us gently into the next chapter, where we begin to consider not just one black hole, but the many. The unseen, the silent population that may fill the early cosmos far more densely than we ever dared imagine. And, as we drift away from the intimate violence of feedback, those winds and jets and waves of radiation that sculpt the fate of young galaxies, we begin to sense a quieter, wider implication settling over the story. Because, well, if most early black holes lived in bursts, if they fed for only a few million years and then slept for 100 million, then what James Webb has shown us is not the exception. It's the hint of a vast hidden population. Imagine the early universe again as it truly was. Dense with gas, tangled in filaments, scattered with young galaxies still trembling from their birth. Now imagine that in many of those galaxies, at their centers, slept giants. Giants too dim to detect. Giants whose periods of brightness lasted only the briefest fraction of their lives. We tend to imagine black holes as dramatic, ever active, ever luminous. But the truth, the uncomfortable truth, is that most of them are not like quasars. They are not roaring. They are not blazing. They are silent. They are invisible. They are asleep. And, well, if a black hole spends 90 to 95% of its time in this state, then the universe we have mapped so far is missing most of them. We have drawn the night sky by the light of the loudest objects and overlooked the ones that whisper. So, when Webb reveals one silent giant from the dawn of time, it naturally forces us to ask, how many more are out there? How many ancient black holes lie dormant, each the remnant of violent, rapid growth, yet now hidden behind the quiet of cosmic winter? This is where the story becomes cosmological, because the implications reach far beyond a single galaxy. They reach into our models of structure formation, into our understanding of mass distribution, into the way we draw the skeleton of the universe itself. If vast numbers of early black holes are sleeping, then the mass budget of the young universe was far more lopsided than we believed. Whole epochs may have been dominated not by stars, but by invisible gravitational wells. Not just scattered objects, but anchors. Anchors shaping the curvature of spacetime, bending the flow of gas, writing the early architecture in ways we couldn't see. And, perhaps the most striking idea is this. These black holes may have been everywhere. Not rare, not exotic, common. It challenges a quiet assumption long embedded in astronomy. The assumption that massive black holes arose only in special places, under rare conditions. But the discovery Webb has given us whispers something different. It suggests that the early universe might have been fertile ground for forming giants. That rapid growth was not an anomaly, but a pattern. That many galaxies hosted monsters, but we have simply failed to see them because they were sleeping. And, well, if this is true, then our cosmic census is incomplete. Very incomplete. The maps we draw, the simulations we run, the equations we rely on, they all assume a number of black holes far smaller than what may actually exist. Imagine updating the cosmic map with these hidden giants. Imagine the gravitational landscape suddenly shifting, deepening, darkening. Thousands, millions of invisible masses altering the flow of matter, altering the evolution of galaxies, altering the emergence of cosmic structures. So, what would that mean? What would a universe filled with sleeping giants really look like? Well, perhaps it would look more chaotic, more turbulent, more intermixed with pockets of quenching and silence. Galaxies would form unevenly, their growth halted and restarted by the pulses of their central black holes. The cosmic web would heat irregularly. Ionization, the era when ultraviolet radiation cleared the fog of neutral hydrogen, would become patchy, uneven, sculpted by the activity of ancient black holes we have never seen. And, the deeper implication is even more astonishing. If early black holes were this common, then they may have played a central role in shaping the universe we live in today. Not a supporting role, a primary one. We often credit dark matter with forming the cosmic scaffolding, and of course it did. But black holes, if numerous, if massive, if widespread, may have woven fine details into that scaffolding. They may have accelerated star formation in some regions, halted it in others, set off chains of mergers, triggered collapses, ignited quasars, built the foundations of galaxy clusters. It's not out there. It's in here, embedded inside the very structure of the modern cosmos. And, well, that idea, the idea of hidden giants shaping everything, forces us to reconsider the timeline of cosmic evolution. It suggests that galaxies did not grow smoothly, but erratically, guided by invisible hands. So, what does this mean for the black hole JWST found? It means that rather than being a rare outlier, it may be one of countless massive seeds, a representative, not a rebel. The first whisper of a story we have not yet heard fully. And this reframes the paradox in a beautiful way. Instead of asking, how could such a massive black hole exist so early? We begin to ask, how many more like it existed? How many are still waiting for us in the deep data Webb will gather across the next years? How many lie in galaxies too faint to detect, in regions too crowded, too dusty, too distant? And, if 95% of ancient black holes are sleeping, then the universe has hidden most of its history in silence. This realization, this quiet shift, is one of the great gifts of modern cosmology. It reminds us that absence of light is not absence of matter. It reminds us that the universe is made not just of what shines, but of what shapes. And, well, once we accept that, another question rises naturally out of the darkness. If these hidden giants were numerous, if they were formative, if they were the unseen architects of early cosmic structure, then what role did they play in the creation of the great systems we see today? The colossal galaxies, the brilliant quasars, the vast galaxy clusters, even the supermassive black holes at the centers of modern giants. Did they begin here? Did they emerge from this population of early sleepers? That question, that bridge between the early universe and the present one, forms the beating heart of what comes next. Because we are no longer talking about one black hole, or even a handful. We're talking about the origins of cosmic architecture itself. And that, leads us gently into the next chapter, where we turn toward the final, sweeping implication of all this. That these ancient monsters, these early giants, may have been the seeds from which the entire large-scale structure of the modern universe ultimately grew. And, as we step from the idea of a hidden population of sleeping giants, something even larger begins to take shape, something that stretches across cosmic time. Because, well, these ancient black holes are not just curiosities. They are not isolated anomalies. They are threads woven into the architecture of the universe itself. And when you pull on one of these threads, the whole tapestry trembles. So, perhaps the right way to begin is with a quiet, simple idea. The early universe did not build galaxies the way we once imagined. We thought stars came first, then clusters, then galaxies, and only then, slowly, gradually, did black holes emerge at their centers. But the discovery Webb has handed us suggests something almost inverted. It's not. It's not stars building galaxies, building black holes. It might be black holes building galaxies, building structure. And, well, once we imagine the early universe with this reversed sequence, everything begins to align. Picture the cosmic dawn again. Hydrogen and helium clouds collapsing into filaments. Dark matter forming the scaffolding. But instead of stars being the first gravitational anchors, imagine massive black hole seeds forming in the densest regions, either through direct collapse or supermassive stellar collapse. These seeds begin to accumulate gas faster than their host halos can form stable disks. They grow explosively, entering binge cycles, pushing out winds, and shaping the gas around them. And the galaxy forms around that. The black hole is not at the end of the process. It is at the beginning. And, when we entertain this picture with sincerity, the modern universe suddenly feels like a long echo of those first giants. The massive elliptical galaxies we see today, red, dead, enormous, may have begun as tiny galaxies dominated by black holes. The quasars, shining brilliantly at later epochs, may have been descendants of these early sleepers, awakened again after mergers fed them fresh material. Even the vast galaxy clusters, held together by immense gravitational wells, may trace some of their early structure to ancient black hole activity. So, the question becomes, how deeply did these early black holes shape the cosmos we live in today? One clue comes from quasars, those dazzling lighthouses of the early universe. They appear surprisingly early in cosmic history. Some burn with the power of 1 trillion suns, and their existence has long puzzled astronomers. How could anything become that massive, that bright so soon? But if early black holes were common, if rapid growth was normal, if binge cycles were part of the cosmic rhythm, then quasars are not exceptions. They are milestones. Signals of a universe where black holes matured quickly enough to light up entire epochs. And, well, this reframing also helps us understand the formation of the largest galaxies. Giant ellipticals, with stars packed tightly into their cores, seem to require extraordinary early growth. Their stars are ancient, their formation periods short and intense, and a black hole capable of heating and stirring the gas could accelerate this process. A massive black hole does not merely sit idly in the center. It regulates the formation of every generation of stars. It's not out there. It's in here, shaping the very bones of the galaxy. Another clue lies in galaxy clusters, the massive assemblies of hundreds or thousands of galaxies. Their centers often host enormous galaxies with supermassive black holes weighing billions of solar masses. These central giants may be the grown descendants of early black holes like the one Webb discovered. Their origins, hidden in the haze of cosmic dawn, may now be slowly emerging as Webb reaches deeper and deeper into the darkness. So, the role of these early black holes may not have been small at all. They may have been foundational, essential, the first architects of the structure we now see. But, well, it's not just the large scale that changes when we accept this picture. It's the timeline, the pace of cosmic evolution. We once imagined the universe taking its time, slowly assembling galaxies, slowly forming stars, slowly building complexity. But these early giants show a universe in a hurry, a universe that rushed into complexity, a universe eager to sculpt structure. And, this forces us to rethink something fundamental, the notion that the early universe was simple. The deeper we look, the less simple it becomes. Instead of quiet clouds and gentle growth, we find turbulence, fire, collapse, black holes that grow too fast, and galaxies that form too early. The cosmos was experimental in its youth, trying out pathways we never anticipated. We grow older, clocks tick, but the universe, in its first moments, sprinted. Another implication emerges from gravitational waves. In the years to come, observatories like LISA will be able to detect the mergers of massive black holes at the earliest epochs. If these mergers are common, if early giants repeatedly collided and coalesced, then we will hear the echoes of their unions rippling through spacetime. And that sound, that gravitational music, will confirm what Webb has hinted, that the early cosmos was filled with giants. And, next-generation telescopes on Earth like the ELT will be able to watch the faintest galaxies at the edge of visibility. If they also contain silent, oversized black holes, we will finally begin to map the hidden population that shaped everything. So, when we look at our own Milky Way, with its serene 4 million solar mass black hole, we may be seeing the descendant of a sleeping giant that once lived through cosmic storms. The story of our galaxy may begin not with gentle star formation, but with a monster shaping the environment before the galaxy even existed in full. It's not a comfortable idea, but it is a beautiful one, because it places us in a lineage of cosmic creativity. It ties our stars, our planets, our lives to forces that roared in the dark long before the Earth was even a thought in the universe's mind. And as we take in these implications, something quiet rises from beneath the science, a sense of humility, a sense that the universe is not only vast in distance, but vast in imagination. It grows structures in ways we never predicted. It hides its greatest architects in silence, and it reveals them only when our instruments finally become sensitive enough to hear the faint gravitational whisper of their weight. And, this brings us gently toward what comes next, because if these sleeping giants truly shaped galaxies, quasars, and clusters, if they served as seeds for the universe's grandest structures, then what does that say about the history of our own place in the cosmos? About the origins of the Milky Way? About the quiet black hole at our center? That, is where the journey leads us next. Toward the final reflections, where the science of cosmics dawn meets the human desire to understand how everything we see, everything we are, emerged from the darkness of the universe's earliest hours. And, as we come to the end of this long journey through the cosmic dawn, something gentle settles in. Like the faint afterglow of a star that exploded billions of years ago, but still, somehow, touches us. Well, you see, this discovery that began with one quiet, sleeping giant has grown into something far larger than the object itself. It has become a mirror, a reminder, a nudge from the universe telling us that the story we thought we knew is, perhaps not the story that truly happened. Because that is the thing about science. We build models, we draw timelines, we sketch the universe in equations and diagrams. But the universe, vast, patient, ancient, does not owe us agreement. It reveals itself slowly, piece by piece, and each piece forces us to shift our understanding. Not just refine it, but sometimes rebuild it entirely. And, this black hole, quietly sleeping at the edge of time, does exactly that. It tells us that black holes did not wait billions of years to grow. They sprinted. It tells us that galaxies did not always guide their centers. Sometimes the centers guided the galaxies. It tells us that the early universe was not slow or simple. It was fierce, dynamic, alive. And, well, most of all, it tells us that the cosmos still holds secrets vast enough to rewrite what we believe. Every major assumption, how black holes form, how fast they grow, how galaxies evolve, how structure emerges, now feels less like a conclusion and more like a question. We grow older. Clocks tick. And still, the universe surprises us. Still, it shows us that the past is stranger than we imagined. Still, it reminds us that we are students in a classroom billions of light years wide. Maybe that is why discoveries like this move us so deeply. Not because they break physics, but because they expand physics. They stretch our imagination to fit a reality grander than the one we expected. They invite us to rewrite chapters we thought were complete. It's not. It's not that the universe contradicts us. It's that the universe is always better, more intricate, more subtle, more beautiful than our first attempts to describe it. And when James Webb shows us a 400 million solar mass black hole asleep in a galaxy too small to hold it, too young to explain it, too quiet to announce it, it is as if the cosmos is whispering, look again, listen again, think again. And, in that whisper lies the heart of cosmology. The humility to accept that the universe is older, grander, more enigmatic than our fleeting lifetimes can grasp. The courage to revise models built over decades. And the wonder, yes, the simple human wonder, of realizing that even now, even in this age of extraordinary instruments, we stand at the shoreline of an ocean far deeper than we can see. So, we end not with certainty, but with possibility, not with final answers, but with a widening horizon. Because if one silent black hole can reshape our understanding of cosmic history, then the universe is likely filled with revelations waiting quietly in the dark. And, well, that is the beauty of all this. The beauty of living in a time when our telescopes can reach back to the first breaths of creation. When each new spectrum, each new pixel, each new flicker of ancient light reminds us that the universe is not finished telling its story. And perhaps it never will be. Because the cosmos is not a book already written. It is a story unfolding, a story still glowing at the edges, a story that invites us, again and again, to follow its light into the unknown. And in that invitation, whispered across 14 billion years, lies the quiet truth of all science. The universe is not simply out there. It is in here, reshaping who we are, what we know, and how we dream. And this discovery, this sleeping giant at the dawn of time, is one more reminder that the greatest mysteries are never behind us. They are ahead.